Dear viewers, welcome and thank you for your constant support by subscribing our channel. In this lecture, you will see another example of analyzing a two-span continuous beam using slope deflection method. So it's a two-span continuous beam, span ABC, continuous beam ABC, span AB equal to 5 meter, BC equal to 5 meters. AB is subjected to non-central point load of 5 kilonewton and BC is subjected to central point load of 8 kilonewton. Step 1, unknown rotations and equations of equilibrium. So for this, the thumb rule is we need to see whether there are any fixed support. So support A is on rollers, B is continuous and C is freely supported. There is no fixed support. So here we'll have theta A, here we'll have theta B and here we'll have theta C. So theta A, theta B and theta C are the three unknown rotations. So when we have three unknowns, we need three equations of equilibrium. So those three equations of equilibrium can be obtained using the principle that other than fixed support, sum of moment at any support is 0. Say for example, the end moment at A is AB. So M at A, MAB equal to 0. That is the first equation of equilibrium. And at B, sum of end moments, MBA this side and MBC this side. So MBA plus MBC equal to 0. And at C, MCB equal to 0. So these are the three equations of equilibrium. Step 2 will be fixed end moments. Span AB subject to non-central point load. In case of non-central point load, the fixed end moment is minus W AB squared by L squared. And this end plus W S squared B by L squared. We know the A and B values are 3 meters and 2 meters. So substituting will get the fixed end moments. And in span BC subject to the central point load. So in case of central point load, the fixed end moments are minus WL by 8 on left side and plus WL by 8 on the right side. W is the load and L is the span. So we'll be getting these values. Then step 3 is the slope deflection equation. So we need to form the slope deflection equation for every span. So every span will have two end moments. So for those two end moments, we need to write the slope deflection equation, which is an equation expressing the end moments in terms of fixed moments and end rotations. So for example, MAB equal to M of AB plus 2EA by L, 2 times theta near plus 1 time theta far. So with regard to AB, A is near end. So 2 times theta A plus 1 time theta B. So M of AB have this value, 2EA by L. You need to substitute the value of moment of inertia. If it is I, you can have as such 2 theta A plus theta B. So here theta A, theta B will exist. So it will not get cancelled. So we'll be getting minus 2.4 plus 0.8 EA theta A plus 0.4 EA theta B. Similarly, MBA will be equal to M of BA plus 2 EA by L, 2 times theta B. For BA, B is nearer. So 2 times theta B plus 1 time theta far. So substituting the values, we will get one equation. Similarly, for span BC, MBC equal to M of BC plus 2 EA by L, 2 times theta B plus 1 time theta C. So substituting the values, we will get one equation. Then MCB is M of CB plus 2 EA by L, 2 times theta C plus 1 time theta B. So that will yield another end moment equation. Then step 4, we need to solve for unknown rotations. So in the first step, we have three equations of equilibrium, namely MAB equal to 0. So substitute the value of MAB, which we have obtained in the third step, that is in the slope deflection equation. So we'll be getting one equation. Similarly, using equation of equilibrium 2, we'll be getting another equation. And then using equation of equilibrium 3, we'll be getting another equation. So we'll be having three simultaneous equations involving three unknown rotations. So solving them, we will be getting the values of EA theta B, EA theta C, and EA theta A. So EA theta C is this, EA theta B. So once we get the value of unknown rotations, that can be substituted in the slope deflection equation back to get the final end moments. So accordingly, MAB equal to minus 2.4 plus 0.8 EA theta A. So EA theta value you have here, 0.4 EA theta B. So getting a value, so roughly equal to 0. Now we should naturally get 0 because A is a freely supported end. And at joint B, you should get balance of moment. So MBA plus MBC equal to 0. So MBA if it is 6.15, MBC minus 6.15 means that we have done all the calculations correctly. So substitute the values of unknown rotations and get the value of end moments. So once the end moments are obtained, mark the end moments in the diagram. So at MAB 0 and MBA we got plus 6.15, so clockwise. MBC minus 6.15, so anti-clockwise. Then we need to find the support reactions considering the free body of span AB and BC to draw the shear force diagram. So consider the free body of AB. We have RA here, load is applied here. We have 6.15 kN clockwise movement and RB1 is here. Why we say RB1 is because B is a common joint, so this side RB1 and this side RB2. So as usual, using sigma V equal to 0, RA minus 5 plus RB1 equal to 0, therefore RA plus RB1 equal to 5. Then using sigma M equal to 0 and taking moments about A, this 5 into 3 plus 6.15 because it acts clockwise minus RB1 into 5 because it produces anti-clockwise movement. So minus RB1 5 equals 0. Therefore, we'll be getting RB1 and RA. Similarly, consider free body of BC. So in BC, we'll have RB2 and RC. And this side, we have N moment of minus 6.15. So mark anti-clockwise. Then use sigma V equal to 0 and sigma M equal to 0. You'll be getting RB2 and RC. So mark the values RA here, RB equal to RB1 plus RB2 and RC value. Then we need to proceed from left to right for finding shear force. For example, at point A, we have two positions P1 and P2. P1 means stand at A, see to the left. There is no force, therefore 0. P2 means stand just to the right of A, just to the right of A and see to the left. So we have left upward force of 0.7. Left up is positive, therefore 0.7. Then come to point E. Position 1 means stand at E itself and see to the left side. Therefore, whatever we have here, this can be transferred here. Then P2 means position 2, that is just to the right of A. So if we stand here, in addition to the value what we have obtained up to this, minus 5. So left it out, minus 5. So 0.7 minus 5, minus 4.3. Then coming to B, position 1, stand at B itself and see to the left side. So this value can transfer. At position 2 of B, just stand to the right side of B and see to the left. So this reaction gets added. So left up is plus. So plus 9.6. We'll be getting this value. Then go to E. Position 1 is stand at E itself and view to the left side. So the value will be coming over here, 5.3. And P2 means just to the right of E and see to the left. So this minus 8 need to be added. Therefore, minus 2.7. Then at point C, at C itself we'll have position 1 at C itself will have minus 2.7. And just to the right of C, if you stand just to the right of C, you'll have minus 2.7 plus 2.7 equal to 0. So you should get always 0 at this end. If you proceed from the left hand, you should end up with 0 at the right hand. Now if you proceed from right hand, and if you should get 0 at the left hand. So at any point, say A, D, B, E, C, we have two values. Just plot the two values, you will get the shear force diagram. So 0.7 here, minus 4.3 here, plus 5.3 here, minus 2.7. So this is the shear force diagram, final. Similar to draw the bending moment also, these reactions will be helpful. So first we should draw this diagram. So I'll tell you how to draw the diagram. So draw this diagram. Say the end moment at A is 0. Similarly at end moment C is 0. Here we have 6.15. So left side you have clockwise moment and right side you have anti-clockwise moment, minus 6.15. So you stand here, apply a clockwise moment and see whether the beam will be pushed up or down. So if you apply a clockwise moment, the beam will be pushed up. Similarly, if you apply an anti-clockwise moment, that will push the beam upward. So you should mark 6.15 here. So and this is the free BMD. So free BMD you need to draw span AB and CD. So we'll be getting this O1 is the maximum positive bending moment in span AB. O2 is the maximum positive bending in span BC. So to get this, we can find bending moment at point D because under the point load, the bending moment will be maximum. So if you find bending moment at D, 0.7 into 3, or if you come from this side, 4.3 into 2, right anti-clockwise plus minus 6.15. So both will yield the same values, O1 value. To get O2, find the bending moment at under the point, this point. So I'm getting O2. So this completes this problem. Please subscribe our channel and join the mission of nation building with concrete concepts through easy learning program. Thank you.